Okay. Hello, everybody. We're going to go over Newton's second law today. This is one of the most famous equations in history because it is a link between force and motion. We first understood a lot of things about motion, but it wasn't until we had Newton's second law that we could put these two together. So the motion equations tell us how things move, and forces tell us why things move. So here is Newton's second law. Now, Newton's second law is actually an equation, but he also wrote it down in words. And I'm going to do a paraphrased version of what he wrote. He wrote that acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So this is sort of quite obvious. The first half is about the force. It means more net force means more acceleration. So if I kick a soccer ball with extra force, it's going to be faster. It's going to accelerate more than if I kicked it with little force. The second half says that if I kick a bowling ball instead of a soccer ball, that bowling ball will accelerate less. That's what inversely proportional means. It means that more mass means less acceleration, whereas directly is they go the same. So more net force means more acceleration, more mass means less acceleration. And that is pretty intuitive. That is something that you would be able to figure out yourself, but it wasn't until Isaac Newton put it into an equation that it was actually a useful information. So here's how he wrote it. When something is directly proportional, it's on the top of the fraction. So delta F, that's net force, or sigma F is net force. It's proportional to A, so it's on top. But mass is it's inversely proportional, so it's on the bottom. So you could picture having a very large denominator would make for a very small number here, and a very large numerator would make for a very large number here. So this is the first way to write the equation, but for simplicity, we're just going to write it like this. They call it F equals ma, but technically you need that Greek letter sigma. This Greek letter sigma always means the sum of. So you can have the sum of the forces. There's a lot of equations it'll be like this. The sum of the masses, the sum of the energies. You can add up all kinds of things. So sigma means sum of. And let's label the rest of these. So this here is net force in newtons. So capital N stands for newtons. This here, of course, is mass, which is kilograms. And that is aceleración. Aceleración. Meters per second squared. So if you're a math person, you'll notice that these units don't match up. We should have the same units on the right as we do on the left. But if you take kilograms times meters per second squared, you get kilograms meters per second squared. So we should also have kilograms meters per second squared on the left, but it's in newtons. We actually do. So basically, what this means, what newtons means, it's a shorthand way of writing this. But this is a weird unit. That doesn't really mean anything to us. So basically, we used capital N as a shorthand way of writing this whole thing. You don't really have to memorize that. It's just kind of cool. So let's actually do some math. Here's our premise. Two friends push a broken down car whose frictional forces push back. Calculate acceleration. Two friends push a broken down car whose frictional forces push back. Calculate acceleration. So here are the numbers for this problem, the numbers that I'm giving you. Very often we just use a box to represent all the forces acting on something. So here's what we have. The two friends are pushing this way. The first friend is pushing with 275 newtons. The second friend is pushing with 395 newtons. Notice that this arrow is longer because they're pushing with more force. And then the largest force of them all is the frictional force. The forces acting on a car are a little more complicated than this in reality, but we can simplify it by just doing one force pushing back. The mass of the car is going to be 1850 kilograms. So we have 275 to the right, 395 to the right, and 560 back. The actual mass of the car is 1850. To calculate acceleration, we're using Newton's second law. That's the whole point of the lesson today anyway. So let's plug in what we know. Now remember, sigma F, it's the sum of all the forces. So we got to add up all three forces. We would do 275 plus 395 plus negative 560. Since it is pointing to the left, it's a negative force. So this whole left-hand side of the equation represents my net force. It represents sigma F. Sigma F is the sum of all three of those. That's going to be equal to 1850 times A. These will be 110 when you combine them. And then we'll divide both sides by 1850. And your answer minimum is 3 sig figs. I'm overachieving today. I'll be doing 4 sig figs. Bless me. Okay. Technically, we should have a plus here. But that's really it. So now that we have the acceleration, we can figure out a lot of stuff about this car. We can figure out its final velocity. We can figure out its distance. We could basically use all the motion equations from last chapter. Let's do another one. Okay, here we go. Ejemplo dos. All right. Here we have a 68 kilogram ice skater. Moving with an initial speed of 9.5 meters per second, experiences a frictional force of negative 20 newtons. How far will they go before coming to rest? Okay, a 68 kilogram ice skater moving with an initial speed of 9.5 meters per second experiences a frictional force of negative 20 newtons. How far will they go before coming to rest? So I wrote all the numbers in the problem because I wanted to avoid drawing an ice skater. I know better than that. I'm not going to embarrass myself trying to draw an ice skater. But the basic idea is they're sliding to the right and friction is pushing back on them. I know this because it's a negative force. The negative means the friction is backwards, and I know friction is always opposite to motion. So if they're sliding to the right, they're slowing down because of friction. And we should expect a pretty big number in our answer because ice doesn't have a lot of friction. The question is, how far will they go? So that means they're looking for delta P. Notice our new equation doesn't have delta P in it. So we're looking at the old motion equations. I'll try to find more information. We need 3 numbers to solve a motion equation. I see right here, initial speed is 9.5. Okay, that's good. That'll help me out. That's VO. They're going to come to rest. All right, that's pretty good. VF is going to be 0. And A is not 9.8. If this ice skater were falling from the sky, yeah, maybe A would be negative 9.8, but they're sliding on the ground here. So the point is, if we use Newton's second law, we could figure out the acceleration. So that's what Newton's law is good for. If something is falling, A is negative 9.8. But if we don't have something falling, Newton's second law can be used to figure out that acceleration. We can only do it here because there's only one force, and A is 68 kilograms. I guess I will have to draw some version of the ice skater. You don't need to do my drawing here. I'm just kind of explaining here. The only force acting on the ice skater is 20, pushing back. There is weight pulling down on the ice skater, but the ground pushes up and cancels that out. So really, the only unbalanced force is the 20 pushing back. So that is sigma F. We'll learn more how to do this later, but I'll tell you now. Sigma F is negative 20. The mass of the skater is 68. And I'm looking for A. Remember, I'm trying to get A because I need 3 numbers to solve a motion equation. So here I'll divide by 68 on both sides, and I'll get negative 0.2941 metros por segundo a la dos. So that makes sense. We want a small acceleration because ice doesn't really slow people down that much. And because of that, we'll have a very large delta P. So I'll write this here, 2941. I'll go looking for my equation. I want the equation that has all 4 of those in it. Of course, on a test, I would provide these equations for you. I wouldn't tell you which one to pick, but you'd find this equation on a list, and you'd be able to pluck it out. And we'll plug it all in from here. Here's what I'll write. 0 squared equals 9.5 squared plus 2 times negative 0.2941 delta P. 0 squared equals 9.5 squared plus 2 times negative 0.2941 times delta P. See if you can do this algebra on your own. Or not. Your notes, your life. So I have 0 equals 90.25 minus 0.5882 delta P. I'll add that negative term to both sides. On the right side, of course, it cancels. Then divide both sides by 0.5882. And as expected, we'll get a large number. 153.4 is my number that I got. So it makes sense. They go, remember, meter is roughly the size of a yard. So this is about a football field and a half. And they weren't even going that fast in the beginning. They were going like, actually they were going pretty fast. They were going like 20 miles per hour. That's what 9.5 meters per second is, something like 20 miles per hour. All right. Let's go on to a third. That second one is probably the toughest of today. Okay. Calculate the acceleration of a 55.1 kilogram skydiver. When F sub G is 540 newtons and F sub air is 400 newtons. Sub means subscript. It means you write a little version of the letter. Calculate the acceleration of a 55.1 kilogram skydiver when Fg is 540 and F air is 400 newtons. So what the heck are these things? We'll learn a lot more about different types of forces in the days to come, but I bet you could figure them out. So this is force of gravity. This is force of air resistance. The thing I hope you can figure out is what direction do they point. So of course gravity points down. So Fg points down, 540 newtons. And air resistance always points in the opposite direction of motion. So air resistance is the thing that slows skydivers down when they have a parachute or if they don't have a parachute. So we're trying to calculate acceleration. Most of you might say, hey, they're falling through the air. So A is negative 9.8, but that's not true. A would be 9.8 if it weren't for this number here. A is only 9.8 when Fg is the only force. Once there's any resistive force, we can't use 9.8 anymore. So basically, yeah, since there's two forces, since there's air resistance, we can't use negative 9.8. So this is a Newton's second law problem in disguise. Sigma F equals ma. When in doubt, just try Newton's second law. It's only 3 letters, so you can figure it out whether or not it's going to work pretty quick. I got to be careful here. It's going to be 400 plus negative 540. The 540 is negative because it's down. So here's what we'll write. 400 plus negative 540. It'll be equal to 55.1. And, I don't know if I did that right. Oh yeah, I did the wrong number. 400. Wait, no, I know this. Negative 140 equals 55.1a. Then we divide both sides by 55.1. And I'll get, there we go, that's better. A equals negative 2.541 meters per second squared. And that's it. If I were to take, I'm kind of curious, hey, what if 540 was the only force here? Don't write this, but let's check it out. Negative 540 equals 55.1a. We divide that. Check it out. We get negative 9.8. So that confirms if that's the only force there, you get negative 9.8. So why is this important? What's the point of Newton's second law? I know that most of you aren't going to walk around and do Newton's second law calculations before you push a car or jump out of a plane or go ice skating. But the point is, it links forces and accelerations. Scientists and engineers, they use this equation for so many different things, especially engineers. I saw a video of a guy that works for NASA. He said that if you want to design spacecrafts, what you got to learn is F equals ma, F equals ma, F equals ma. This is the basis of rocket science. What forces are acting on the rocket to get it up to speed? It's all about changing that speed. That's what acceleration is, a change in speed. I wanted to show you something. This is an advanced equation. We won't do calculations with it, but it is interesting that it's so similar to what we did. Something I came across the other day. It's the force on a wind turbine. So a wind turbine, it's those renewable energy things. Oh, that's horrible. That's a little better. It's those big windmills on those big wind farms, like this. The equation for the force, so energy is all about forces causing motion. Most of energy, like energy production, is just spinning something. So there's a force that the wind is pushing on here with, causes it to spin. So what's the force that the wind is pushing with? It is this. It's the Greek letter rho times, I'll just use capital A, times V times delta V. This is actually V average. So it looks a little bit similar. Acceleration is a change in velocity, so it makes sense that delta V would be here, a change in velocity. What about this? This is the density of the air passing through. It's the area that this is spinning through, and it's the average velocity. The meaning of this, I wonder if you have a guess. The meaning of this is close to mass. It's mass flow. It's the rate, it's the amount of kilograms of air. If you combine all three of these, it's the amount of kilograms of air passing through per second. The amount of mass, kilograms, the amount of kilograms of air pushing through per second. So if we extend that a little bit, it's the mass per second. And look at this. Delta V over T, delta V over T, that is our definition from lesson 2 point something, 2.4, maybe 2.3. That is the definition of acceleration. So check it out. F equals ma. Boom. It shows up everywhere. Any force that you talk about is some variation of F equals ma. So that's just a cool relation of it. With gravity, friction, you can always make it some version of this. We won't use this for calculations, but it's pretty cool. And that's our show. Remember, the things to memorize are back here. Let me show you the thing I actually gave you. Here's what you gotta memorize. Memorize these units. You may as well memorize this equation because it's only 3 letters. And remember that this means sum, the sum of. Sigma F means the sum of forces. Sigma M means the sum of masses. And that is all. Thanks for watching. If you have questions, hit me up. Cheers.